Okay, so here we are on quiz number 10. It says match these values of R with accompanying scatter plots. Okay, so remember what an R value means on a scatter plot. If you have an R that is like 0.9, that means the dots go up almost like a straight line. If R is 1.0 perfectly, the dots go up in a perfect line. If R is like negative 0.8, then they go down pretty much kind of like a straight line. I guess that's not the best straight line. And if their R is negative 1, then they go down as a perfect straight line. And if R is something around 0, like 0.1 or negative 0.1, basically 0, the dots are just everywhere. They're not a straight line at all. So that's the idea. R is the linear correlation coefficient. Kind of running out of room there. And so I'll just leave that. So it's the linear correlation coefficient. In other words, if R, here, let me write one more thing. So if R coefficient, linear correlation coefficient. So if R is close to positive 1, then the dots go in a line with a positive slope. If R is close to negative 1, then it goes in a line with a negative slope. If R is close to 0, positive or negative, then the dots are not in any line. All right. Yeah, let's go through it. So first off, so scatter plot 1, we're looking here. Do those dots look like they're in a line? Yeah, they really do. They look pretty much like a line. Now, is it a perfectly straight? Is it a line going up to the right, or down to it? We always mean as you go to the right. So when it comes to talk, because if we're not clear, if we go like that, that's a line going down. So positive slope is a line going like that. Negative slope, this is positive up here, is a line going like that. Right? As you go to the right, does it go up or down? So this line is going down, and are they perfectly lined up? Not perfectly, but they're close. So I'm going to go with negative 0.994, as opposed to this one, scatter plot number 5. Those are perfectly straight down, aren't they? So that one is the negative 1. That makes sense. This one's negative 1. This is negative 0.994. They're almost a perfect line. Okay, scatter plot number 2. Let's do number 2 now. Those look like nothing. They're not a line at all. Which one of those numbers is closest to 0? This one. Minus 0.389. That's basically, it's just close to 0. We don't care that it's negative, positive, whatever. It's close to 0. How about scatter plot number 3? This one sort of looks like a line through the, we're talking about the line through the middle, the best fit line. The best fit line's kind of through the middle, but it's not super linear. There's some of these dots are really off the line, aren't they? So that's going to be the 0.769 because it's positive, right? So it's going up, but it's not all that linear. And then finally, we've got the last one, which is 0.994, because that's positive, almost a perfect line going up, 0.994. There we go, recognizing the linear correlation coefficient on a scatter plot. Okay, so here we are on number 2. So listed below, if you read all the words, basically it says these are internet users in various countries per 100 people. So it's basically percent. Per 100 means percent. So 78% of the country uses the internet in this country. 80% of this country uses the internet. 56% of the country uses the internet. And the numbers on below are how many scientific award winners there are per 10 million people. So basically what we're seeing in this data set is that countries that have higher internet usage also have more science. This is science award winners. Countries that have lower internet have less science award winners, generally. There's some exceptions to this. Okay, anyway, so we need to put the data. The first thing they want us to do is get a scatter plot. So how do we do that in our calculator? So to get a scatter plot on our TI calculator, put the L1, put this information in L1, and this information in L1, this information in L2. So put that in your calculator. Hit stat and data. No, I'm sorry, edit, stat, edit, etc. Stat, edit, and I'll go ... Put L1 and L2 in the data banks. And then you have to hit, so that's step one. So step one. Step two, you've got to hit second stat plot, which is it's above the Y equals key in the upper left-hand corner. Hit second stat plot, and then you've got to hit enter when you're on plot 1. And then you've got to turn it on. It probably already is on, but turn on plot number 1. And then on the type of graph, you've got to select the first type. Well, how I should say it. How about this? You'll see 6 different types of graphs. And this is the one you want. So you want to select that one because that one is the dot plot. You'll see little dots on it. That's the scatter plot. So you're telling the calculator, I want to graph a scatter plot. So your X list, I'm assuming your X list will be L1. Your Y list will already be L2. You're good, and then you just hit, after you got all that ready to go, then you just hit the zoom button, which is at the middle top of the screen, and then hit 9, which stands for zoom stat, and which basically means do a stats graph for me. And you will get a scatter plot. And so then pick the right scatter plot. It should be this one. You'll see that on your screen. So that's the first thing to do. Okay, and I'll call your attention to the exam 4 notes. Here they are. Exam 4 notes. And see, there is graphing a scatter plot, which the instructions we just went through. So remember, the exam 4 notes will be super helpful to you. Okay, let's get back to it. Now we're doing the linear correlation coefficient, R. How do we get that? Back to the exam 4 notes. Here we go. Finding the linear correlation coefficient R. Put the data in L1 and L2. We've already got that. Hit Stat, Calc, and choose 4. So hit Stat, go over to Calc, and go down to 4, which is linear regression. Hit Enter a couple times, and you'll get your R value when you do that. And I'm doing it now as we speak. We get an R value when we do that of 0.794. That should be your R value rounded to 3 places. It'll say R equals. All right, now it wants me to do a hypothesis test. Next, determine the null and alternative hypothesis. What are we testing? Determine whether there is sufficient evidence to support a claim of linear correlation. In other words, is there a linear relationship here between internet users, like countries that have more and more internet users, percentage of internet users, do they also have more and more awards for science award winners? Is there a linear relationship? Right here is the dots. It kind of looks like a line sort of fits through the middle of those dots, kind of, sort of. Not super great. This R value, 0.794, that's close to positive 1. Remember, positive 1 would be, remember positive 1 back here. Here's positive 0.994. That's almost a straight line, perfectly straight up. So that R value is 0.794. That's close to 0.1. So kind of a linear. These dots look like they're kind of in line. This 0.794 is kind of close. It's somewhat, so I'll just say somewhat close to 1.0, but not great. So somewhat, I'll say a little close to 1.0. So maybe, it's a maybe. So anyway, so what do we do for the null and alternative? Let's go to the exam 4 notes. Testing for linear correlation, a linear relationship. How do you test if two variables, the variables here are internet users and award winners in a country? Is internet users, right? See, the x-axis is internet users, the y-axis is award winners. Do they have a linear relationship? Well, we see the dots right here. Are these coming from a line and they're just sort of barely off that line, or are those dots so spread out that there's really not strong evidence of a line relationship, linear relationship? That's what we're trying to test. How strong is the evidence that internet users and award winners, having internet users in your country and science award winners is a linear relationship? The dots fit a straight line relationship. How much evidence is there for that? We can look at the scatter plot. We can find the R value. Want that close to 1.0. It's a little bit close to 1.0. But then here comes the official test, hypothesis test. What does it tell us to do? Put the data in L1, L2. Already got that. Linear regression t-test. Your null is R equals 0. That's no linear relationship. And and then not equals 0. Right, because if R is 0, there's no linear relationship. And so if R is not 0, then there's more of a linear relationship. So no linear relationship when R is 0. If R is not 0, there's more of a linear relationship. That's what we're testing. It's how we always test for remember, the null hypothesis is what you assume, like a court of law. Assume innocent, assume R equals 0, no linear relationship or correlation. We assume that the two variables have no linear relationship. And then we see what the evidence says. So HO is, now they're using that. Now what happened to R? That is a Greek R. It's called rho. I know it looks like a P to you. You're thinking that's not a rho, that's a P. Yeah, it's a Greek letter. It's pronounced rho. It is a Greek R, basically. We always use Greek letters. I don't know if you've noticed, for the alternative, for the hypothesis test, the null hypothesis and the alternative hypothesis. When we use the Greek, what we're saying there is we're saying the true value. So R is the sample, and rho, it's kind of like a P with a bendy part, is the Greek true parameter. I'm not going to quiz you on these names at this point. But, the R is the value. We took a sample. We took whatever this is, 5, 6 countries. 1, 2, 3, 4, 5, 6. 6 different countries, right? 6 different countries. Took some data. We got an R from our sample of 6 countries, which was that R value. And now we're going to test, do you think rho, which is like the real R, the truth of all countries in the whole world, that's what the Greek letters always are. They're the true parameter. That's, you always take a sample because you're trying to find something out about the true relationship. So we always use the Greek letters to represent the true relationship, English letters to represent the sample. So what's the truth? Is there really a linear relationship in all countries in the world between internet users and award winners? Does the data from these 6 countries provide strong evidence or weak evidence? Let's see. So rho here is equal to 0, right? The null hypothesis is always equal, and the alternative is not equal to 0. It's always that way when you're testing for a linear relationship. This is basically R. It's just the Greek version of R. It's the true relationship, not just the sample. Okay, that's what we're testing. So let's run it on our calculator. So we just do linear regression t-test. So now we'll do that. So linear. So we go to stats, go over to test, go to linear regression t-test. We're wondering if there's a linear relationship. Hit enter. Choose the X list should be L1 because that's where you put your X values, right? These are the X values. And these are the Y values, which are in L1 and L2, the X and Y values for the X-axis internet. Right, this is the X-axis, is the Y-axis. Y-axis is the award winners. So the Y list is L2. And you choose the not equal 0 option. And then you calculate. Hit the buttons. And the test statistic should come out to be, I got 2.61, and the p-value 0.059. All right. And so what's our significance level? There it is. Significance level 0.01. So this is greater than 0.01, not less than 0.01. Let's go to a fresh screen. So what did we get here? We got equals 0, not equals 0. Test statistic 2.61. P-value 0.059. When we did linear regression t-test. All right, so that is greater than 0.01, the significance level. So the P is not low, right? The P-value is greater. So HO does not go away. The P-value is not low, so HO does not go. So what was I? So we keep HO. So that's weak evidence, right? Always this is strong evidence, but we didn't have strong evidence. We only had weak evidence. So evidently, this is not, these dots, this 0.794 correlation coefficient, basically this data is not strong data, not strong enough to conclude beyond a 1% chance of luck. That's what we're trying, right? That was the significance level, that this data was in a line. In fact, we said there was a 5.9, almost 6% chance that these data came out kind of lined up by luck. That's just too much of a chance of luck. We don't believe there's strong evidence that they're really they have a linear relationship. We don't believe that internet users and award winners have there's not strong evidence they have a linear relationship. Because the p-value of the linear coefficient is greater than the significance level, there is not sufficient evidence to support the claim that there's a linear correlation. between internet users and scientific award winners. There we go. On to number 3. Find the regression equation, letting the first variable be the predictor, x variable, using the listed actress-actor ages in various years. Find the best predicted age of the best actor winner, given that the age of the best actress winner that year is 63 years. Is the result within 5 years? All right, so this is interesting. So they want me to find the equation of the regression line. Find the equation of the regression line. How do we do that? Guess where I'm going to go look? Exam 4 notes. So here we go, exam 4 notes. Predicting, finding linear correlation. Oh, and linear regression equation. So how do we find, there's what we want, the linear regression equation. Put data in L1, L2. Let's do it. So put this data in L1. So clear out the old data from the last problem. Put L1 and L2 data in your calculator. And then what? Hit stat, calc, and 4 linear regression. So then hit, I'll write it over here, hit stat, calc, and what was it? Stat, calc, and 4 linear regression. AX plus B. Right? Yeah. All right. And the linear regression equation is y equals ax plus b, as it says there. So when you do that, when you hit those buttons on your calculator, it's going to tell you, so you're going to get y equals ax plus b, and it'll tell you, what's it going to tell you? It's going to tell you that the A is minus 0.200 and the B, it's going to tell you is 51.9. That's what you get on your calculator when you do hit the linear regression button. So what does that mean then? This is supposed to be an A here. What that means, and you got to watch out because they're reversing it. See how they're putting the X on the right side and your calculator puts it on the left? So you got to watch out for that. So your calculator is saying whatever A is, that's what goes next to X. So that'll go right here. And whatever B is, that's what goes not next to X. That's right here. So the question reverses the direction of your calculator. So watch out for that. Okay, now we come down and they say, okay, the best predicted age of the best actor. Okay, we're gonna do the best predicted age of the best actor. Okay, so how do we do this? Let's go back to exam 4 notes. What does it say? Here we go. We're on number 9. And it says there, predicting with the linear regression t-test. Okay, how do we do it? Well, if p is less than 0.05, you do one thing. If p is greater than 0.05, you do another. So clearly, we need p. How are we going to get p? We got to do the linear regression t-test. So let's go back. So on this one, you're going to have to hit linear regression t-test. So step 1, hit linear regression t-test on your calculator under the stat tests. So go to your stats, test, linear regression t-test, hit enter. It's going to do the same things it did before. X list is L1, Y list is L2. And frequency, that's always 1. And you're going to choose the not equals 0 option. That's what we always do. Okay? And then when you hit calculate, you'll get a p-value. And the p-value I get, let me change the color up here. The p-value I get when I do that is 0.259, blah, 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 blah. And they go, okay, if your p-value is less than 0.05, mine is not. If your p-value is greater than 0.05, so my p-value is certainly greater than 0.05. What does that mean? That means, remember what the null is always? It's that R equals 0. Remember, the null is always equal. The alternative, not equal. Remember what equals 0 means? No linear relationship. And H1, if R does not equal 0, it implies there's a linear relationship. So, all right, so what does that mean? So we got a p-value that's greater than 0.05. Greater than 0.05. That means the p is not low, so the HO does not go away. You keep the HO, which means there's no linear relationship. So when you get a p-value greater than 0.05, the p is not low, so the HO does not go away. You keep HO, which means there's no linear relationship. We really believe that R, the correlation coefficient, the linear correlation coefficient, we really believe it's close to 0, right? The evidence here is weak, right? It's not strong. Down here would be strong evidence. There's weak evidence. So these two variables, age of the actress, age of the actor. So this is when people win the Best Actor, Best Actress award every year. So in 1 year, the Best Actor wins, 28 years old. The actress is 28, the actor is 43. Next year, the actress is 30, the actor is 36. Next year, etc., etc. Well, we're saying there's no connection there. There's no linear connection there, right? The evidence is weak. The p-value is high. It's not low. It's greater than 0.05. P is not low. The HO does not go away. We keep HO. Evidence is weak. There's no linear relationship. We do not believe that the age of the actress allows you to predict the age of the actor. It's just not true. There's no linear relationship. There's not strong evidence of a linear relationship there, right? You can't just look at this data and go, oh, I see, they're all connected. You know, when the actress is older, so's the actor. When the actress is younger, it's just not true. There's no linear connection like that. It's not true. So there's no linear relationship. So see what they're trying to do? They're trying to give us this number here, which is 63-year-old for the Best Actress. So if next year the Best Actress winner that year is 63 years old, if she's 63, can we use that to predict how old the Best Actor is going to be? No way. There's no connection there. There's no linear relationship. That's what this p-value is telling us. It's a high p-value. It's not low. The HO does not go away. We stay with the HO. The evidence is weak. There's no linear relationship. So that 63 cannot be used to predict the Best Actor age. So so what does this mean? So you cannot use the 63. The 63 does nothing for you because there's no linear relationship. No linear relationship. You cannot use the 63. Well, then what do? Let's go back to the instructions. If the p is high, there's not strong evidence of a linear correlation, so don't use the equation. But instead, what do then? Hit stat, calc, one variable, L2, and use X bar. In other words, you just go with the average. So let me write that down. So instead, we hit stat, calc, hit stat, go over to calc, choose one variable, and next to one variable, choose L2. That's really important. You know how you get L2? You have to hit second and 2. That's super important that you do L2 there, right here, not L1, L2. Why? Why L2? Because remember, L2 is the actors. We're trying to find, right? We're trying to find the predicted age of the actor. The actors, not actress, actors are L2. They're saying the best predicted age of the actor, the best actor, when the best actress is 63. We know her age. The best actress is 63. We don't need L1. We've got L1. But what we want is the best predicted age of the best actor, L2. So put in the one variable stats, put in L2, as it says right here, L2, hit the buttons and find the X bar, which is the average, right? X bar is the average. So what does X bar show when you do that? I'm getting X bar equals 44 point whatever. So that's our estimate for the best actor. Notice, what did we just do? This is average actor age. So in other words, they said, hey, this next year, the best actress that won is 63 years old. How old do you think the best actor is going to be? And all we did was say, well, I don't know. Just look at all these numbers in L2, right? These are all L2, and just give me the average. Because there's no relationship to the 63 to the actress's age. They're not connected in any way, right? There's no the P was high. There's no strong evidence of a linear relationship. So all we did here was take the average actor's age, the average of the L2 values, and we said, you want me to predict an L2 value? There you go. It's just whatever. My guess would be it's just the average actor's age, which is 44. That's my prediction of the actor's age. I'm not going to use the 63 at all. There's no linear relationship. Well, then it goes on down and it says, okay, well, here's the actual results. Is the result within 5 years of the actual best actor? He was 37 years old. That was the actual guy that won. He was 37 years old. We predicted 44. 44 minus 37 is 7 years away. We were 7 years away from the correct prediction. So what does that mean? No, the predicted age is more than 5 years greater than the actual winner's age, right? We predicted 44. The actual winner was 37. We were more than 5 years away. We didn't guess within 5 years. Okay, so on the next problem number 4, we're going to see where we get a p-value that is below 0.05 and what you do about that. See that right here, this option. We're going to do that one next. Let's take a look at it. Okay, so here's some data. The data show the bug chirps per minute at different temperatures. Okay, so in other words, have you heard about this before? This is actually true. When the temperature outside is 87 degrees, the crickets chirp 1241 times in 1 minute. When the temperature goes lower, like 76 degrees, they chirp less. When the temperature goes higher, they chirp more. Now, it's not a perfect relationship. We can see some exceptions in this table. So the question is there a strong linear connection here between chirps and temperature? Basically, the hotter it is, the faster those crickets chirp. The bugs, whatever bugs it is, they chirp faster at higher temperatures, slower at lower temperatures. So the question is there strong evidence of a linear relationship between these two? So, and then they're asking us for the regression equation. How do we do that? Let's go back to the table here and how do you find a regression equation? Well, this is kind of messy here. So we're talking about let me get rid of all this marks I've been doing. So coming back here, this is number 7. Find a linear regression equation. Put the data in L1, L2, stat, calc 4. So let's do it. So put the data in L1, L2, hit stat, calc, and choose 4, when you do that, which is linear regression ax plus b. So choose that, hit the buttons, and when you do, what you'll get, remember it's giving you y equals ax plus b. It tells me the a is 0.0476, and it tells me the b on my calculator is 31.26. And now careful though, because over here, notice the a is right there next to x, so I got to put a right here, don't I? 0.0476, and the b is not next to x, so the b needs to go here. 31.26. See the rounding? They say round the x coefficient, round the thing next to x to 4 places. See, I did that 4 places. And round the constant, the other thing, to 2 places. I did this to 2 places. Okay, so there's the equation. That's the linear connection. But now they say, okay, what is the best predicted temperature for a time when the bug is chirping at a rate of 3,000 chirps a minute? All right, how do we do prediction? Let's go back to our exam 4 notes. Here it is, predicting with linear regression. Got to get the p-value. So we got to do the linear regression t-test. So let's do it. We got to come over here, and we're going to do linear regression t-test. You know, under stat and tests. So you hit stat, go over to test, linear regression t-test. It's the usual x list is L1, y list is L2, and choose not equal to 0, and calculate. And remember what we're actually testing when we do this. The null hypothesis and the alternative. The null is always that the r equals 0 and there's no linear relationship. And H1, the alternative to that, is r does not equal 0, and there is a linear relationship. Remember how evidence goes. It takes strong evidence for this, weak evidence for that. Okay, what's my p-value? I'm getting a p-value that is 0.026. What's the significance level? Right there, 0.05. That is certainly less than 0.05. So that p is low. So the HO must go away. Bye-bye, HO. Evidence is strong, isn't it? That p is low. There's a low % chance of luck. So these data seem to be, there's strong evidence that they're in a linear relationship. Basically, the higher the temperature goes, the more them buggy boys chirp. There's a linear relationship. They're pretty much in a straight line. We could see the scatter plot. I'm not going to bother since they're not asking me, but you could do the dots and they'll be pretty much in a straight line. So this is what the hypothesis has proved here. There is a linear relationship, strong evidence, because that p is low. There's a very low chance of luck. This data came out so lined up that we believe there's strong evidence that temperature and chirps have a linear relationship. Okay, so what does that mean then? So that means you can listen to how fast the bugs are chirping outside, and it's almost like a thermometer. You can know the temperature. The faster the bugs are chirping, the higher the temperature goes. Again, not a perfect relationship, but strong evidence of a linear relationship. Okay, so now they're saying, all right, suppose you hear 3,000 chirps a minute. I'm not sure how a person could hear 3,000 chirps in a minute. What would that be, like 50 a second? It's impossible. But anyway, we'll pretend some kind of computer can read 3,000 chirps a minute, 50 a second, by the bugs. They're going crazy chirping outside that's really crazy fast. 3,000 chirps every minute. If we hear that, or the computer audio is programmed to record that and tells us the buggy boys are chirping 3,000 chirps per minute outside, what's the best predicted temperature? Well, how do we predict? Well, that's what we did last time. Remember, if the P is less than 0.05, you do one thing. If it's greater than 0.05, you do another. What's our p-value? Our p-value is 0.26. It's less than 0.05. Last time, on this problem, the p-value was 0.25. It was higher than 0.05. So we have a different deal this time. So we have a p that is low, then there's strong evidence of a linear relationship, correlation. So use the linear equation and plug in x to find y. See, last time, the last problem on number 3, there was not strong evidence. And so we did not use the equation. We just found the average. We just said, hey, just give me the average of the L2 values, and I'll just take the average, and that'll be my best guess. But if P is low, if P is less than 0.05, then there's strong evidence of a linear correlation. So you can use the linear relation. This is the connection between the two variables, between x and y. So you can use that. Plug in x, find y. So I'm going to use that relationship. So here's step number 1. Do the linear regression, find the p-value. Step 2, use y equals ax, whoops, that's an a there, ax plus b. This equation right here, use that. All right, so that's this equation. Use that, so it's y equals 31.26 plus 0.0476x. Again, they have x in front, the thing has x in the back, whatever, same equation. Plug in, now the 3,000, what is the 3,000? That's x. The 3,000 is your, how do you know that's x? Because chirps, that's chirps, right? 3,000 chirps. Chirps is x. Temperature is y. It's xy. So chirps is 3,000. So plug in right there 3,000. So you're going to get y equals 31.26 plus, my little plus sign's getting off, plus 0.0476 times 3,000. I'm going to do that on my calculator right now too. And I'm getting 174.1, and they want me to round it, 0.1. They say round to 1 decimal place. So what is that? That's the temperature. Remember, the y is temperature, the x is chirps. This is a linear, there's strong evidence of a linear relationship. So if you hear 3,000 chirps a minute outside, if that's your x, that's your chirps, that you can use that to predict the temperature using this equation. That's what a linear relationship tells you. These two things, chirps and temperature, are in a relationship, a linear relationship. Just plug in x right there, plug in the chirps, the 3,000 right there, and then 31.26 plus 0.0476 times 3,000 comes out to be 174.1. That must be the temperature outside. That's kind of hot, 174 degrees. So this is really kind of a silly example. So if you hear the buggy boys chirping 3,000 chirps a minute, don't step outside. It must be 174.1 degrees outside. What's wrong with this predicted value? A, it is unrealistically high. The value 3,000 is far outside the range. So you look up here at our chirps. We didn't have any chirp numbers around 3,000. The highest we had was like 1,241. So you can't use a number that's way outside of the data you collected. It's just craziness. So that's what's crazy about this example, but otherwise, it's a good example of how two things can have a linear relationship. We proved strong evidence that they have a linear relationship, and then we used that linear relationship to plug one of them in, the chirps, to calculate the temperature. That's how that works.